Welcome back everybody to second year physical chemistry, and today we will deal with non-volatile solutes and modeling the activity. What will we cover today and why? Can we understand activities a bit more intuitively by modeling it? So we will be dealing with something called the Margules equations. The second thing we will deal with is a very interesting problem. So far we have discussed measuring the vapor pressure of different solvents and solutes in order to obtain activities. What happens if your solute is non-volatile? For example, if you've got sugar or sucrose and you dissolve it into water, the sucrose is not going to have a vapor pressure. What do you do then? What will you need? You'll need the previous lectures on chemical potential of ideal solvents and solutions, as well as the Gibbs-Duhem relation. In terms of mathematics, you need to remind yourself about integration. And from Atkinson's physical chemistry, you'll need to consult the big section of simple mixtures and the subsections of the properties of solutions and activities. So modeling activity using excess functions. What are excess functions? Well, let's begin to understand what happens when we mix substances. So this holds true not just for solutions but also for gases. So we can think of two substances, say oil and water, and we are going to blend them together. What happens to the energy? Let's be very specific. What happens to the chemical energy? So let's consider what the Gibbs free energy would be before we blend our two substances together. And it's simply given Gi, where I is for initial, is equal to the sum of the chemical potentials times the number of moles for each component. And the chemical potential is the pure state of the liquid in our case. So that should be fairly easy. Now, what we'll do is we will blend our two substances together to get a final Gibbs free energy. And that means that the chemical potentials would now have changed. So we need to substitute for the chemical potential the full chemical potential equation, which includes the mole fraction component, as you can see. As an aside, since I used the example of oil and water, it turns out you can mix oil and water, though it takes a little bit of doing. The picture you see here is taken from the website, which you can see at the very bottom of the slide. It's quite an interesting read and video. But let's continue. So we've got ourselves a final Gibbs free energy and an initial Gibbs free energy. And what we'll do is we'll just take the difference and we call this the Gibbs free energy of mixing, delta mix G. And it's equal to nRT, where N is the total number of moles, that's N1 plus N2, is equal to the mole fraction 1 times ln x1 plus x2 ln x2. You can also determine the same mixing functions for the entropy and the enthalpy of mixing, which you can see here. The entropy of mixing is very similar to the Gibbs free energy of mixing, but you are missing the temperature variable, and the enthalpy of mixing is equal to 0. Now what's interesting to understand is the functions you are seeing here are for the ideal case. Alright, the great reveal, excess functions. An excess function is then when you take the previous mixing functions for ideal case and subtract something from them, basically to get the real behavior. So it takes the general form of x, your function, we denote with E for excess equals delta mix X minus delta mix X ideal. And from this, we can define something called a regular solution or regular solutions. Regular solutions are defined as solutions where we have the enthalpy or the excess enthalpy is equal to the delta mix enthalpy minus its ideal case, which we set equal to N, the number of moles, eta, a dimensionless parameter that captures interactions between the substance in 1 and 2, R, T, X1 and X2. So how does these excess functions now relate to activity? Well, we identify the Gibbs free energy of mixing for a real solution as what we just saw previously, but we change the mole fraction or inside the Lin functions to an activity value. However, for regular solutions, we can write the Gibbs free energy of mixing, and what you'll notice is it looks like the ideal case, but we've got this additional sum part of eta x1, x2. Now, what you want to do is you want to reconcile these first two equations. And when you do that, you get two equations out, which is known as the Margules equations, which will show that the log of the activity parameter or coefficient for 1 is equal to eta mole fraction of the second component squared. And you get the reverse equation for the activity coefficient for the second substance. With this, you can then derive the following two equations. One, for example, the activity for one substance, and hence the pressure for one substance. What happens? Well, let's see what happens in real life, or at least what happens with this model we've constructed to represent real life. Here's a figure taken from Atkins. Well, you note that at the bottom axis is the mole fraction of substance A or substance 1, and on the y-axis you have your relative pressure, which is the pressure divided by the saturation pressure. Now, when your eta parameter equals 0, what you get back is a straight line for mole fraction for the vapor pressure versus mole fraction. And that is just Raoult's law. For positive values of eta, you get endothermic mixing, which means you've got unfavorable solute-solvent interactions. And these give higher vapor pressures at low concentrations versus your ideal case. So you can see the values where you see the values on the graph, in the middle of the graph next to the lines, 0, 1, 1.52, 2.53, those are the positive values for eta. For negative values of eta, you get an exothermic mixing or favorable solute-solvent interactions. And it gives higher vapor pressures, it gives lower vapor pressures at low concentrations versus the ideal case. And you can see there's one case written down there where eta is equal to -1. So who was Margules? He was born in 1856, died in 1920. He was an Austrian, and he was a mathematician, physicist, and chemist. Now, we've dealt with trying to understand activities, or at least attempting to model them. What we'll now deal with is how do you measure the activity for a non-volatile substance? And to do so, we have to go back to the Gibbs-Duhem equation. And they are back. There you go, the dynamic duo. And to remind you, here is the first equation is our Gibbs-Duhem result. And we are going to go to constant pressure and temperature conditions, which means that 0 is equal to the sum of all moles times 2 changes in the chemical potential. Now, you can rewrite that equation completely for the case of two substances in terms of activities, and what you'll get is minus x1 d log gamma 1 equals x2 d log gamma 2. So basically, if you change the activity of one substance, you change the activity of the other. So if you know the change of the activity of the one substance, you can infer the activity of the other. So, for example, you have table sugar in water. You are able to measure the vapor pressure of water, and you know the mole fractions of both the water and the sugar. How do you do that? Well, you integrate. Here's just some rearrangement where you just divide both the Gibbs-Duhem result by x2, for example. You recall that the mole fraction of 1 plus the mole fraction of 2 has to equal 1. So you just do a substitution, and now you integrate. The procedure, if you look at this integration equation, the procedure is to plot that kernel, that x1 on 1 minus x1, and then numerically integrating the area underneath the curve. Now, if you don't quite understand how this works, we will deal with this in a workshop question. So what are the key concepts I want you to take away? Well, first of all, there are these things called excess functions, which is defined as xe equals x delta mix x minus delta mix x ideal. Excess functions can help you understand activities of solvents and solutes, but they both have to be volatile. For example, you get the Margules equations, which are presented here. And finally, you can use the Gibbs-Duhem result to determine the activities of non-volatile solutes. Now for the quiz. When two substances are mixed to form an ideal mixture, your Gibbs free energy change is given by delta mix G equals nRT multiplied by x1 ln x1 plus x2 ln x2. Is this chemical energy change driven by energetics or entropy? A. Energetic changes, or B. Entropic changes. Question number 2. Can the Gibbs-Duhem equation be used to determine the activities of a volatile solvent and solute system? Yes or no? And finally, can the Gibbs-Duhem equation be used to determine the activities of a solid solution? Yes or no?